last week we have started the topic of sports field studies. Okay, so we learned what do we mean by sports field study, why do we do it, we want to find out the choice of the driver, and to do or to find out the choice of the driver, then we have some restrictions. Okay, that the distance which you are taking should not be more than 1000 feet. There is a range for the flow as well, that the flow should not be more than these values, otherwise the driver choice will not be found. Once you collect the data, where we can use it to update our speed limits, we can use it for design, we can use it for investigation of accident sites. Then what are the important parameters which we can calculate for the speed data? We have the mean, the standard deviation, the 85th percentile, the median, and the pace. The speed data can be collected in different ways. There are some methods which are manual, some are semi-automated, and some are automated. But the important thing is, once you collect the data, you have to divide it in the form of groups. Okay, so you will make a speed, or you take the entire speed range and put it into smaller intervals. Okay, we call them speed groups, and for each group then you should have the number of observations, and we call these observations as frequencies. Okay, so we have speed groups and we have their frequency. Then I showed you this table which has the sample data. It shows you the speed groups, the middle speed of the group, the number of observations which are taken in the field for each group, then percentage of values in each group, okay, which is the value upon the total number of values, cumulative percentage frequency, which is addition of the frequencies. Then we have n into s and n into s square. What is n here? What is s? Tell me. S is middle speed and n number of vehicles, cars. Okay. Using this data, we can plot these two graphs. First one, percentage frequency distribution. Second one, cumulative percentage frequency distribution. So the first one, middle speed on the x-axis, percentage frequency on the y-axis. You plot the points and then you try to make a best fit line that can be as close to the points as possible. And second one, maximum speed on the x-axis, cumulative percentage frequency on the y-axis. Again, plot the points and then try to make a best fit line. And these best fit lines, the first one, it should start at 0 and at 0. Okay, so we had made the had some extra groups which had 0 observations, one at the start, one at the end. Okay, same thing here. It should start at 0 and end at how much? 100. Okay, cumulative cannot be 100. Less than 100 or more than 100. So these are the fixed points. So your best fit lines should have these fixed points. So up to the graph is considered, preliminary. Okay, you have to make speed groups. You have to note down their observations. Okay, frequencies, and then make the graph. This is considered like default. This much you have to do. Okay. After that, the real calculation starts. So the calculations we perform, or the numbers which we get from the speed data, we call them descriptive statistics. Okay. So the statistics means numbers, and descriptive means what? When we say this is describe something, describe means what? Information. Explaining. Okay. So these are the numbers, or these are the statistics which explain the behavior of driver in terms of speed. Okay. So we try to know the behavior of the driver in terms of their speed, at what speed they like to go, and so on. Okay. So we call them descriptive statistics because they describe, explain, or provide information about the driver's speed. Okay. So these statistics can be of two types: central tendency and dispersion. Okay. So about the data, or about the driver's behavior, we want to find out two things. What is the range of normal speed of the drivers? normally, or most of the drivers are driving around which speed? To know that, we need central tendency. Okay, central tendency. So the normal speed of the drivers is approximately in the center of the range. The normal range is in the center. Okay, so that's why we call it central tendency. So the numbers or statistics which tell you about the normal range of data, we call them central tendency. Okay, then we have dispersion. Can you give me another word for dispersion? Separation. Okay. Anybody else? If I say the data is dispersed, it is separated, or something? Variation. Okay. So dispersion means variation. What are the extremes of the data? What are the extremes of the data? So the numbers which tell you about the extremes, the extreme values of the data, or how separated or varying the data is.
Outliers.
Outliers. Okay. So we want to know the normal range, and we want to know the outliers or the variation in the data. Clear? Okay, the extreme value. Okay. So we start with central tendency. The first measure of central tendency, what we know is mean. Okay. So mean is usually around the center. Okay. So how do we calculate mean normally?
Summation over
number of values. Okay. This is how we do it. But the problem is our data has speed groups and frequencies. Okay. So if you do summation upon number of values, where are the number of values? Tell me. Where are the number of values? Number of vehicles, right? If you do this upon total, it will give you average number of values. I am trying to find out what? Mean of speed. I don't want mean of number of values. I want mean of speed. Okay. So these are the speed columns, right? Upper, lower limit, middle. These are the speed columns. Okay. If I take the mean of any of these columns, then who set these values? Who set these values? No, these values. The speed values. Who set them? Say again? Yeah? I was looking for it. Anyways. So they are set, right? They were set by someone. Okay? So that person can set anything, right? You can set anything. You can change the speed groups. So your average will change, your mean will change. It should not be according to some person who is setting the values, right? It should be according to the observations. So if I just take the observations, it will give me average number of observations, not the speed. If I just take the speed, then it is the set value which is done by the observer. I have to combine both of them. Okay. So how they are combined, you can see the equation on the top. Okay. So it has n and s both. Okay. Like you said, n is the number of values and s is the middle speed. So both are combined. Okay. What is capital N? Total number of values. This value, 368. Okay. Capital N is total number of values, which in this case is 368. So can you give me the mean here? So even the summation is given here, 17736. .2. Okay, clear? Any problem? Okay, so you cannot apply the simple mean equation to the frequency distribution data because you have to combine the values and the data. number of values and the data. So you have to combine them. This is how we do it. Clear? Okay. The rest of the parameters for central tendency will be taken from these graphs. Okay. So I already told you how these graphs are plotted. They are coming from that table. Okay. The next parameter is median. Now what is median? What is the median? The middle value. Okay. So middle value means what? 50% of the data is under, 50% of data is above. Okay. So we can also call it the 50th percentile. Okay. We can call it the 50th percentile as well. So percentile is a value which is in a particular order in the data. So 50th percentile means it is at the 50th order, at the half of the data. If we say 85th percentile, that means this is the 85th value in the data. Got it? Okay. So whenever we have to take a percentile, we'll use this graph. Remember. Okay. Whenever we have to take the percentile, we'll use this graph. So in this graph, on the x-axis, I have the top speed of the group, the upper value of the group. On the y-axis, I have cumulative percentage. Okay, so for any percentile, we'll use this graph. Clear? Now, which percentile I'm looking for? 50. So, which percentage I'm looking for? 50. Okay, so I'll draw a line from 50 to the curve and then drop a perpendicular. This. Okay, so this becomes my median. Clear?
Yes.
Okay, so median means 50th percentile, the half of the data. For any percentile, we'll use a cumulative percentage frequency curve. So you go to the percentage of 50, go to the curve, drop the perpendicular, your value is median. Clear? Okay, any problems? Now, the next one is mode. Okay, what is mode? Most common number, right? The most repetitive value. So the most repetitive value will have the highest frequency, right? The most repetitive value will have the highest frequency. Agreed? Okay. Which graph gives me frequency for different values? The first one. Okay. Second one is cumulative. So it's not for each value. It's addition of all the values, right? So I will use the first one. Now I'm looking for which value? The one which has highest frequency. That means top of the curve. As frequency is top of the curve, right? So you go to the top of the curve, drop a perpendicular. Where? X-axis, y-axis. X-axis. Okay. And you will get the value which you will get will be your mode. Clear? So mode means the highest frequency value. Go to the frequency curve. Take the value which has the highest frequency. Clear? Okay. Now, this is the value which has highest frequency. Okay. This is the value which has the highest frequency. I am asking you for the value of which has the highest frequency, not the frequency of this value. I am not interested in how many times the value is repeated. I am interested in which value is repeated the most. Got it?
Yes.
Okay. So the common mistake in terms of all these parameters, whenever the students take any value from the graph, they mix the x-axis and the y-axis. Okay. For example, median. Median is which percentile? 50, right? It is always 50, right? Will it change? No. So I already know which percentile is it. I'm asking for what? Which value has 50th percentile, right? Clear? Huh? The students will say, okay, median 50th percentile. So median is 50. Median is which value has 50 percentile. Clear? Same thing with mode. Okay. Which value has the highest frequency? 47. And what is the frequency of this value? Can you give me an idea? How much is the frequency? 18. I'm not looking for 18. Okay? I don't want to know how many times it's repeated. I want to know which value is repeated the most. Got it? Clear? Okay? So we are looking for speed values. Okay. Then the next measure of central tendency is pace. Okay? Let me remind you, pace means it's a 10 mile per hour interval which has more values than any other interval. It's a 10 mile per hour interval which has more values than any other interval. Clear? Okay. So, which graph I will use? I am looking for frequency for values. Which graph I am looking for? The first one. Okay. So, now if I draw a line here, okay, from here to here. Okay, so I draw this line. What is the length of this line? Can you tell me? 10, right? Starts from 30, goes up to 40. Okay, so if I put this line on the graph, under this line I will find an interval of 10, right? Which is my pace. Clear? If I put this line on the graph, under the line there are two values and the difference between them is 10. Okay? Am I looking for any 10?
The highest.
The highest one, right? Now where is the highest?
Inside the graph and
No, inside the graph, where is it? Huh? Here, right? Somewhere here. Okay. If I move on the other side, if I move on the left hand side, is the frequency increasing or decreasing? If I move the line towards the left hand side, is the frequency decreasing or increasing? Huh? Decreasing, right? It's going down, the curve is going down. Okay. And what will happen if I go to the right hand side? Same, right? So this is the position which will give me the maximum frequency. If I try to shift here or there, the curve is going further down. So there is no other interval on which I can fit this line on the graph, and this will give me the highest frequency. Okay. So we take a scale or a line or a box, it's shown in the box here. Okay, anything. And you try to fit it around the maximum frequency point. The top one is the maximum frequency, right? So you try to fit this line of 10 miles per hour on your graph around the maximum frequency point. Okay? And this is how you do it. So your line is fitted here. Now if you take the values which are under the line, this is your pace. Okay? So if you go below this point, you get 42.1. If you go below this point, you take 52.1. Clear?
yes.
Okay. So first of all, you need something which has a length of 10 miles per hour according to the graph. Okay. And then you try to fit that thing around the mode value, the top value on the graph. Okay. The points where this 10 mile per hour line will fit is your pace. Clear? Okay. Any questions? Anybody?
Why did we choose 10 again?
Sorry?
Why did we choose 10 as a
10 is standard. 10 is standard. It's default. It's fixed. Somebody did it in the book. Yes.
In the exam, you measure the length of a box of 10 miles per hour, and then you will put the order inside the graph.
Yeah. You can do it with the book. Yes. Okay. Any other question? Okay. What else? Yeah. So we have discussed 4 measures of central tendency. Which ones? Tell me.
Simple.
4 measures of central tendency. Which ones? Median, mode, pace, mean. Okay, mean, median, mode, and pace. All of them are measures of central tendency. Okay, there is no other tendency. Clear? Okay. The next one is measure of dispersion. Okay, the first one we will discuss in measures of dispersion is standard deviation. Okay, a standard deviation, just for the sake of explanation, you can understand it as the difference between the mean and the data itself. So data has 100 values, you take the mean, you will get 1 value. Okay, then you take the difference of this mean from the data. Okay, so that difference is known as, or the average of that difference is known as standard deviation. Okay, clear? Now, we have equations to calculate standard deviation. This is the first one, which applies to normal data. Any data which you have, like you have values, okay, speed values, 100 speed values, or temperature values, or something like this, you will use this equation to calculate the standard deviation. Okay, but our data has what? Frequencies. Okay, so you can see here, there is no frequency here. Okay, the frequencies are not mentioned here, so we cannot use this equation. The same problem which we had with the mean. Okay, so we have to combine the speed and the frequencies. Okay, so this is the equation which we use. What is small n? Number of vehicles where? Number of vehicles for? Total number of vehicles in the middle where? For each group. For each group. Okay, number of vehicles for each group. What was S? Middle speed. Okay. X bar? Average or the mean. Okay, we already calculated. So what is capital N? Total number. Okay, total number of values. Total number of values. Okay, so summation of small n will be equal to what? Total number of values, which is capital N, right? Summation of n is equal to capital N. Clear? Okay, so this is the main equation. If you open the bracket and wherever you have summation of n, you replace it with capital N wherever you can. Okay, then you will get this equation. Okay, so this one and this one, they are the same. This one is with the bracket, this one is without the bracket and with the summation. Clear? Okay, but both of them will give you the same answer. Okay. So the equation is this. What is the standard deviation? Tell me. Everything is given here. The summation is 868448. The mean 48 point, how much? 1 or 2? 48.2. What? Okay, clear?
Yes.
Okay. Now this is measure of dispersion, right? This is a measure of dispersion. We are also calling it that it tells you about the variation in the data. Okay. So if this number is higher, that means variation is high. Okay, because then the data is more away from the mean. Okay, so that means variation is higher. Clear? Okay.
Yes.
Okay. Next measure of dispersion is percentage of vehicles in the pace range. Okay, so we already found the pace, right? The pace is between 42.5 and 52.5. We already know this. Okay, now what we want to know is how many drivers are in this range. We know they are higher than other ranges. We know, but how much is it? Got it? Okay. So for example, somebody says this range has the highest number of drivers compared to other range. What is that highest number? Is it 60%? Is it 65% or 70%? So I'm looking for that percentage now. Clear? Okay. I know it is higher than others, but how much is it exactly? Okay. So I know the values of the pace. Okay. I start from the top, 52.5. Okay. So I'll come to this curve, the second one with cumulative percentage. I'll locate here 52.5. So 52.5 is somewhere here. Okay. From 52.5, I go to the curve and find out its percentage. That comes out to be 77%. So the cumulative percentage for 52.5 is 77%. Okay. Now remember, this is cumulative, right? So 77% is not for 52.5. It is for 52.5 and less. Okay. So this is from 0 to 52.5, everybody. 0 to 52.5, everybody has total of 77%. Clear? Okay. Then I do the same thing for the lower limit, lower value of pace, which is 42.5, somewhere here. Okay. So I go to the curve, find out its percentage. For this data, it is 16%. Just trust me. No problem. Okay, it is 16%. Okay. Again, is this value for 42.5?
No.
No. This is from 0 to 42.5. Okay, got it? So 0 to 52.5, 77%. 0 to 42.5, 16%. How many between them? You will take the difference. Okay? Clear? Any questions? Okay, so for this data it is 61%. Okay? Any problems? Any questions? So 61% of the drivers are in this range. That means outside the range are only how many? 39%, right? Okay, so what we were saying, pace has more percentage than other ranges is true. Okay. Let's say I gather another data set and I plot it. I find out the pace. I find out the percentage. For that data set, the percentage is 70. For this data set, 61%. For that data set, 70. Which data has more variation? This one or that one? This one has more variation. This one has more variation because it has less values in the middle. So more values outside. Values in the middle are increasing, that means variation is getting less. The outliers are decreasing. The outliers are decreasing. Here the outliers are more than 30%. If this percentage is 70, that means outliers are only 30%. Okay. So this number increases, variation decreases. Got it? Clear? Everybody? Okay. Another measure of dispersion is 85th percentile and 15th percentile. Okay, 85th percentile and 15th percentile. This range is also a measure of dispersion. Okay, why? This is, according to research, the true definition of outlier. Anybody who is out of this range is statistically called an outlier. Okay, so any driver who is driving at more than 85% is an outlier, or any driver who is driving at less than 15% is an outlier. Clear? Okay. Research shows that the normal drivers, whatever you call as normal, you have your own mental picture of normal in your head, right? Normal drivers do this, okay? They honk at everybody, they use phone while they are driving, and so on. Those normal drivers are in this range, okay? And anybody who is outside the range is insane, mad, okay? Put him in the hospital. Clear? Him or her. Clear? Okay? Now these are percentiles, right? Which graph gives me the percentiles? Which graph gives me the percentiles? The second one. Okay, cumulative. Which percentile I am looking for? 85 and 15. Okay, so simple. Go to 85 here, curve, perpendicular, 85th percentile. For 15 percentile, go to 15%, curve, perpendicular, it will give you the values. Okay, for this data, it is 54.7 and 42.4. Clear? Okay. Now you see these values have a difference of 12, around 12 between them, right? If these values get close to each other, the variation is increasing or decreasing? Huh? If they are getting closer, so variation is decreasing, right? Decreasing. Okay. Clear? Because the normal drivers are very close to each other. Okay, the normal range is very close to each other, so variation is less. Okay, clear? The range of normal drivers is very short, so that means variation is less. Okay, if this range is bigger, larger, wider, that means variation is more. That means even the normal drivers have very big difference between them. Got it? Okay. So this tells you the range of normal drivers. Another application of this range is to calculate standard deviation. You can use these two percentiles to calculate the standard deviation as well. Okay. So we have already seen one equation of standard deviation. This is another equation. Okay. So if you use this equation and these are the percentiles, tell me the value of standard deviation. Six point what? 1. Okay, so you can see the values are very close, right? Same. There is small difference between the fractions. Okay, and this is possible because they are different methods. This is different equations. You can get some difference. Okay, but it will not be like this one is 6 and the other one is 16. Okay, they should be close to each other. If they are very far from each other, that means there's a mistake. Clear? Okay, yes. You just did. You didn't do. Okay, he just did. You can do as well. Huh? Yes, I can do. Right? But if you have both methods available, which one is more reliable? This one. Why? Huh? Both are reliable. More reliable. Which one is more reliable? Huh? I cannot see it in your hand. That one. Huh? This equation. Why this one? The answer is right. Huh? Yeah, it's more difficult, right? So it takes more time. This is the only reason. Okay? Anything which takes more time, is more difficult, is more reliable. Okay? It's a life lesson. Keep it in mind. Okay? Now, you remember the graph, the first one, okay? The frequency distribution graph, okay? You look at the shape of the graph, it's symmetric, right? You have a peak and then the graph goes down on both ends. Okay, so we call this as a bell-shaped curve. This is called as a bell-shaped curve. Okay, bell-shaped curve means that it is symmetric. Okay, so if you have a frequency distribution data and you plot it and it looks symmetric like this, makes a bell-shaped curve, then we call this data as normal distribution data. A data which has a symmetric shape of distribution, frequency distribution, we call it normal distribution data. Okay, and again, according to research done in many fields, it's not about only traffic. They have done research in many fields. So according to them, any data which is taken from the real world, speed or temperature or wind velocity, pressure, whatever, if you take enough samples of a data from real world, then it should be symmetric like this. It should follow normal distribution. You should have normal distribution. Okay, clear? So obviously, speed data is taken from real world, real cars, right? You should real cars. Okay. So then speed follows normal distribution. Okay. So if I have to show that the data follows normal distribution mathematically to someone, this is how we do it. So X is my data. It follows N. N is what? Normal distribution. This X has a mean of 40 and this X has a variance of 25. Okay, so the N letter means normal, indicates normal distribution, and the numbers inside the brackets are mean and variance. Now mean we already know, we have calculated it. Variance is the square of a standard deviation. You were saying something else?
No, standard deviation square.
Yeah. Okay, so variance is, if you take the square of standard deviation, then you will get variance. Clear? Okay. So if I want to write about my data, that it follows normal distribution, how will I write it? Tell me. Yeah, use S, right? I'm using S for speed. Okay. Now what? N. And then 48.2. And how much is this? That's the thing, it's not 36. See? So 0.1 can go up to 1.2 if you square it. Okay, that's why you ask you to make groups. Clear? Any question up till now? Okay. Then we have, so you plotted the data and its normal distribution, any data, it's normal distribution, and you found that that data has a mean of 0 and a variance of 1. You have a data set, you plotted it, you got the bell-shaped curve, it's symmetric. When you calculated the mean was 0, and you calculated the variance, it was 1. If you have a case like this, then we call it standard normal distribution. Okay? So what is a standard normal distribution? It's a normal distribution, obviously, which has what?
Mean equals 0.
Mean equals 0 and variance equals 0. Clear? Okay? Now what is the advantage of, and we represent it with letter Z. Z or Z. Okay? So Z or Z represents that normal distribution which has these parameters. Okay? Now what is the advantage if I found a case where the data follows standard normal distribution, it has 0 mean and so on, then my work will become easier, because for a Z distribution, the values of percentiles and mean and median and mode are known. Okay, there are tables available for that. There is a graph which is already plotted for Z. So you don't have to make these things again. Okay, but my problem is the speed data. So can the speed data be Z? We can convert it, but can it be Z? Can there be a case where it will have these? Why not? Because
Not zero.
yeah, the mean cannot be 0, right? For speed, mean cannot be 0. To have 0 mean should have negative and positive values both. We cannot have negative speed. Okay, so I cannot use a Z tables and graph directly. Okay, but I can convert my data to Z. Okay, this is the conversion equation. So you take your data, value in your data x. X is the value in your data. To convert, minus mu upon sigma. What is mu? Mean of x. What is sigma? Standard deviation of x. Okay, so this equation is used to convert x to z. Once it is converted, then you can use the Z table and Z graph and so on. Okay, these graphs you can Google them, they are available, they are in the book. Even Excel can be used to calculate the Z values. Even MATLAB can be used to calculate Z values. Okay, any software which deals with numbers can give you the values for Z and its percentiles. Clear?
Yes.
Okay. Okay. Yeah, somebody told me in the class. I don't know if it is. I don't know. Okay. This mean, 48.2, it is for how many values? 368. Okay, 300 something values, right? Okay. If I take more data or another data set, it will be different, right? The mean standard deviation will be different. Okay. So these values apply only to a sample. This is the mean of the sample, standard deviation of the sample. But I'm not interested in this sample. These 300 drivers don't mean anything to me. I'm interested in all the drivers. So I want to have an idea about all the drivers. Okay, the entire population of drivers. Okay, so what is the range of mean for all the drivers? I have the range for sample, and I want to know it for all the drivers. So what do we do? First thing you have to calculate E. E is called as standard error. E is called as standard error, which is S upon root of n. S is standard deviation of your data, and n is number of values in your sample. Standard deviation of the sample, number of values in the sample. Clear? Okay. So first thing is you have to calculate standard error. Standard error tells you the error in your observations. The error in your observations. Clear? Okay. Then to find out the range of mean for the entire population of drivers, we use a theorem which is called as central limit theorem. Okay. What does central limit theorem say? You have seen the normal distribution curve, right? The normal distribution curve. So there is the middle of the curve, right? Okay. So you go to that middle, then you do 1.96e plus 1.96e minus. Find out the center value, the mean, then do 1.96e plus 1.96e minus. You will get a range, right? According to central limit theorem, this range is 95% of the data, or 95% of the mean of the data. So if you take samples 100 times, 95% of the times your mean is here. Okay? Huh? You take the center value of your sample. From that center value, add 1.96 into E and subtract 1.96 into E. The theorem says the range which you will get after adding and subtracting, this is 95% of the mean of the data. If you took 100 times, samples 100 times, and you calculate mean each time, 95% times your values will be in this range. Okay? Clear? Then another point in the same theorem is Don't do 1.96 E. Do 3 times E. Now you will get more bigger range, right? Okay. So according to central limit theorem, this range is 99.7% for the mean of the range. So if you took 100 samples, 99.7% is the chance that the mean will be in this range. Clear? Clear? Okay. Now which will give you more, which will make you more confident? This mean of one sample or this range? Range, right? So we call this range as confidence interval. This is called as, the range is called as confidence interval. Okay? And these are 2 percentages, right? So the percentage for which you are calculating the confidence interval, we call that percentage as confidence level. So the percentage is called as confidence level, and the range of this percentage is called as confidence interval. Clear? Clear? Okay. So we already have the mean. If you do mean plus minus 1.96 E, where E is this, you will get 95% of the range of mean. If you do 3 times E, you will get 99.7% of the range of mean. Clear? Okay. So bring these values tomorrow for this data set. Okay. You already know the mean. You already know the standard deviation and the number of samples. Okay. Any questions? Any problems? Abdullah Samir, Salman Hussain, Shahad Khalid, Aisha Muhammad, Muhammad Jafar, Rida Hassan, Muhammad Abdullah, Ahmad Dahir, Ali Adil, Zainab Ahmad, Haya Abdullah, Zainab Ali On, Reem Fahim, Hussain Abdul Basit, Shahad Yasin, Muhammad Ibrahim, Yusuf Abdul Nasir, Wadia Yasin. Thank you.
Thank you, Doctor.